Introduction. Hello Rohit, how are you?
Good morning, Dad. I am good.
What are you doing?
I am doing chemistry, Dad.
Whoa, chemistry is a good subject to study.
Thanks, Dad.
Do you know that everything is made up of atoms?
How is it possible, Dad? And what is atom?
Atoms are the basic building blocks of ordinary matter. As you know that everything is made up of molecules and atoms join together to form a molecule.
Okay, Dad. What kind of materials are there in the atoms?
Atoms consists of electrons, protons and neutrons and central core which is called nucleus.
It sounds interesting. Can you tell me more of it?
Yes, Rohit. In this lesson, you will study the structure of atom. Objectives. At the end of this lesson, you will be able to explain subatomic particles, discuss atomic models, define atomic number and mass number, define isobars and isotopes, explain developments leading to the Bohr's model of atom, explain Bohr model of hydrogen. Subatomic particles. Discovery of electron. A discharge tube is long glass tube. This tube is fitted with metal electrodes on either end, across which high voltage can be applied. The tube is also connected to a vacuum pump for controlling the pressure of gas inside the discharge tube. There is a coating of phosphorescent material behind the anode. When the gas pressure inside the discharge tube is 1 atmosphere, no electric current flows through the tube. If the gas pressure is reduced to about 10 to the power minus 2 atmospheres and a potential difference of about 10,000 volts is applied to the electrodes, an electric current flows and at the same time light is emitted by the gas. If the gas pressure is reduced to 10 to the power minus 4 atmospheres, the emission of light ceases. Instead, the tube glows, fluorescence with a faint greenish light. This fluorescence was caused due to the bombardment of the walls of the tube by rays emanating from cathode. These rays were called cathode rays. These rays were found to consist of negatively charged material particles called electrons. Properties of cathode rays. Cathode rays travel in straight lines. An object placed in the path of cathode rays casts a sharp shadow. It shows that cathode rays travel in straight line. Effect of electric field. When electric field is applied to a stream of cathode rays, they are deflected towards positive plate. It showed that cathode rays themselves are negatively charged. Effect of magnetic field. When magnetic field is applied perpendicular to the path of the cathode rays, they get deflected in the direction expected for negative particles. This further confirmed that cathode rays are negatively charged. Charge to mass ratio of electron. On simultaneous application of electric and magnetic fields applied perpendicular to each other, it is possible to adjust the two fields so that the cathode rays strike the fluorescent screen at the same position as they do when neither field is applied. The value of charge to mass ratio of the electrons was found to be 1.76 into 10 raised to the power 8 coulombs per gram. The E by M ratio for the particles in the cathode rays was found to be same irrespective of the nature of cathode or the nature of the gas taken in the discharge tube, thus showing that the electrons are universal constituent of all matter. Charge on the electron. R.A. Millikan found the value of charge on electron by oil drop experiment. The oil droplet enters the apparatus through a small hole and are allowed to fall in between two charged plates. The motion of the droplets is observed with a microscope. The space between charged plates is irradiated with X-rays. The X-rays ionize the molecules of air. One or more electrons thus produced may be absorbed by an oil droplet. Thus, the charge on an electron E is equal to 1.6 into 10 raised to the power minus 19 coulomb. Mass of the electron Me is equal to 9.31 into 10 raised to the power minus 31 kilogram. Discovery of protons and neutrons. Goldstein in 1886 used a perforated cathode in a discharge tube. On passing the electric discharge at low pressure, he observed a new type of rays carrying a positive charge streaming behind the cathode. These rays were named as anode rays or canal rays. Properties of anode rays. The charge-to-mass ratio of the particles in the anode rays was found to depend upon the nature of the gas in the discharge tube. It was observed that E/M ratio was maximum when hydrogen gas was taken in the discharge tube. This indicated that the positive ions formed from hydrogen are lightest. These lightest positively charged particles were named protons. The neutrons was discovered by Chadwick. He made alpha particles to strike on beryllium, and neutral particles are emitted, and these were called neutrons. Atomic models. Thomson model of atom. He proposed that an atom consists of a uniform sphere of positive electricity in which the electrons are distributed more or less uniformly. This model of atom is known as the plum pudding model or raisin pudding model. Rutherford's nuclear model of atom. Rutherford's nuclear model of atom, alpha particle scattering experiment. The experiment involved the bombardment of a thin sheet of gold by alpha particles. These particles were obtained in the form of a narrow beam by passing through a slit in a lead plate. A circular screen coated with zinc sulfide ZnS was placed around the foil to detect the deflection suffered by alpha particles. Whenever an alpha particle struck the screen, a tiny flash of light was produced at that point. Observations. Number 1. Most of the alpha particles, nearly 99%, passed through a gold foil undeflected. Number 2. Some of the alpha particles were deflected by small angles. Number 3. A few particles were either deflected by very large angles or were actually reflected back along their path. Explanation of Rutherford's nuclear model of atom. He explained his observations as follows. Number 1. Since most of the alpha particles pass through the foil undeflected, it indicates that the most of the space in an atom is empty. Number 2. Alpha particles, being positively charged and having considerable mass, could be deflected only by some heavy positively charged center. The small angle of deflection of alpha particles indicated the presence of a heavy positive center in the atom. Rutherford named this positive center as nucleus. Number 3. Alpha particles which make head-on collision with heavy positive center are deflected through large angles. Since the number of such alpha particles is very small, the space occupied by the heavy positive center must be very small. Main points of Rutherford's nuclear model of atom. Main points of this model are: Number 1. Most of the mass and all the positive charge of an atom are concentrated in a very small region called nucleus. Number 2. The nucleus is surrounded by electrons which are revolving around it at very high speeds. The electrostatic force of attraction between electrons and the nucleus is balanced by the centrifugal force acting on the revolving electrons. Number 3. Total negative charge on the electrons is equal to the total positive charge on the nucleus, so that atom on the whole is electrically neutral. Number 4. Most of the space inside an atom is empty. Atomic number and mass number. The number of unit positive charges on the nucleus of an atom of the element is called atomic number of the element. Atomic number of an element is equal to the number of protons in the nucleus of its atom or the number of extranuclear electrons. Generally, it is denoted by the letter Z. Atomic number Z is equal to number of protons is equal to number of electrons. Mass number. Total number of protons and neutrons in the nucleus is called mass number of the atom. It is generally represented by the letter A. Mass number A is equal to number of protons plus number of neutrons is equal to number of nucleons. Isobars and isotopes. Mass number and atomic number of an element are indicated as: isotopes of an element are the atoms of the element with same atomic number but different mass numbers. The three isotopes of hydrogen can be represented. The atoms of different elements which have same mass number are called isobar. Drawbacks of Rutherford model. Number 1. According to electromagnetic theory, a charged particle when accelerated emits energy in the form of electromagnetic radiation. According to Rutherford's model, electrons are revolving around the nucleus. This means electrons would be in state of acceleration all the time. Since electrons are charged particles, so electrons should emit radiation, and as a result, they get slowed down and finally fall into the nucleus by following a spiral path. Rutherford's model failed to explain stability of atoms. Number 2. It does not explain the distribution of electrons around the nucleus and does not tell us anything about their energies. Number 3. Rutherford's model also failed to explain the existence of certain definite lines in the hydrogen spectrum. Developments leading to Bohr's model of atom. Wave nature of electromagnetic radiation. According to the Maxwell's wave theory of light, light is transmitted in the form of electromagnetic waves. These waves are associated with oscillating electric field and magnetic field. These two fields are perpendicular to each other and also to the direction of propagation. Parameter of the wave. Wavelength. It may be defined as the distance between two neighboring crests or troughs of the wave. It is represented by lambda and is generally measured in angstrom units or nanometers. 1 angstrom is equal to 10 raised to the power minus 10 meter. 1 nanometer is equal to 10 raised to the power minus 9 meter. Frequency. It may be defined as the number of waves which pass through a particular point in 1 second. It is represented by mu. Its units are cycles per second or hertz. Velocity. The distance traveled by a wave in 1 second is called velocity of the wave. It is denoted by letter c. The frequency and wavelength are related to the velocity c by the relation c is equal to mu into lambda. Its unit is meter per second. Wave number. It may be defined as the number of wavelengths per unit length. It is equal to the inverse of wavelength. It is denoted by mu bar. Its unit is the reciprocal of wavelength unit. It is generally expressed as 1 by centimeter or 1 by meter. Mu bar is equal to 1 by lambda. Amplitude. It is the height of a crest or depth of a trough of a wave. It is generally expressed by the letter A. The amplitude of a wave determines the intensity of radiation. Particles nature of electromagnetic radiation. Planck's quantum theory. Wave theory of radiation cannot explain the phenomena of photoelectric effect and black body radiation. Black body radiation. An ideal black body is a perfect absorber and perfect emitter of radiation. When such a body is heated, it becomes red hot. In other words, it emits red-colored light. As the temperature is further increased, the color of the radiation emitted changes from red to yellow to white and finally to purple as the temperature becomes very high. This implies that wavelength of radiation emitted by a black body decreases with increase in temperature. Consider the graph from right to left. At a given temperature, intensity of radiation emitted increases with decrease of wavelength, reaches a maximum value at a given wavelength, and then starts decreasing with further decrease of wavelength. Particle nature of electromagnetic radiation. Planck's quantum theory. Planck's quantum theory of radiation. Radiant energy is emitted or absorbed not continuously but discontinuously in the form of small packets of energy called quanta. The amount of energy associated with a quantum of radiation is proportional to the frequency of radiation, where h is a constant known as Planck's constant and is equal to 6.625 into 10 raised to the power minus 34 joules second. A body can emit or absorb energy only in terms of the integral multiples of quantum, that is, E is equal to nh nu, where n is equal to 1, 2, 3, 4, etc. Photoelectric effect. Photoelectric effect may be defined as the phenomenon of ejection of electrons from the surface of a metal when light of suitable frequency strikes it. The electrons thus ejected are called photoelectrons. When light of particular frequency strikes the metal surface, electrons are ejected from the metal surfaces, which are detected by the detector. For a particular metal, there exists a threshold frequency V0, such that at frequencies below the threshold, no electrons are emitted, no matter how large the intensity is or how long the radiation occurs. The number of photoelectrons emitted per second is directly proportional to the intensity of the incident radiation but does not depend upon its frequency. According to Einstein, electrons in metals are held by some attractive forces. To overcome these forces, certain minimum amount of energy is required, which is characteristic of the metal. This is called photoelectric work function W0. W0 is equal to h nu naught. Einstein equation can be written as h nu is equal to h nu naught plus Ke. Ke is equal to h nu minus h nu naught. Dual behavior of electromagnetic radiation. The photoelectric effect could be explained considering that radiations consist of small packets of energy called quanta. These packets of energy can be treated as particles. On the other hand, radiations exhibit phenomena of interference and diffraction, which indicates that they possess wave nature. So it may be concluded that radiations possess dual nature, that is, particle nature as well as wave nature. Evidence for the quantized electric energy levels. Atomic spectra. The phenomenon of splitting of a beam of light into radiation of different frequencies after passing through the prism is called dispersion, and the pattern of radiations obtained after dispersion of beam is called spectrum. In case of dispersion of sunlight, the 7 colors obtained change from violet to red without any discontinuity, which means each color bends into the other. Such a spectrum is called continuous spectrum. Emission and absorption spectra. When an element is excited by some method, such as by heating, by passing electric current, or by passing electric discharge, the atoms of the element emit electromagnetic radiations of definite frequencies. The arrangement of these radiations in the order of increasing wavelength or decreasing frequencies is called emission spectrum of the element or atomic spectrum. Atomic spectrum of an element can be used to identify the element and is sometimes called fingerprint of its atoms. Atomic spectra of most of the elements consists of number of bright lines separated by dark bands. That is why atomic spectrum is also known as line spectrum. Absorption spectrum is the spectrum formed by the electromagnetic radiation that has passed through a medium in which radiation of certain frequencies is absorbed. Line spectrum of hydrogen. When an electric discharge is passed through hydrogen gas, its molecules dissociate into hydrogen atoms. The excited hydrogen atoms, thus produced, emit electromagnetic radiations of discrete frequencies. The spectrum obtained consists of a large number of sharp lines. Each line corresponds to a particular frequency of light emitted by hydrogen atoms. The lines in the emission spectrum of hydrogen are classified into 5 series as follows. Lyman series. It is in ultraviolet region. Balmer series. It is in visible region. Paschen series, Brackett series and Pfund series. These are in infrared region. The spectral lines are expressed in terms of wave numbers. Then the lines in the visible region obey the formula. Wave number is equal to 1,09,677 into 1 by 2 square minus 1 by n square per centimeter, where n is an integer equal to or greater than 3, that is, n is equal to 3, 4, 5 and so on. After this, Rydberg gave a more general formula which is applicable to all the series in the hydrogen spectrum. Wave number is equal to 109677 into 1 by n1 square minus 1 by n2 square per centimeter, where n1 and n2 are integers, such that n2 is greater than n1. For a particular series, n1 is constant. The value 109677 per centimeter is called Rydberg constant for hydrogen. Bohr's model for hydrogen atom. Bohr's model of atom is based upon quantum theory of radiations. Main points of this model are: The electrons in an atom revolve around the nucleus only in certain selected circular orbits. These orbits are associated with definite energies and are called energy shells or energy levels. These are numbered as 1, 2, 3, 4, etc. or designated as KLMN etc. shells. Only those orbits are permitted in which the angular momentum of the electron is a whole number, multiple of h by 2 pi, where h is Planck's constant, that is, angular momentum of the electron. MVR is equal to nh by 2 pi, where n is equal to 1, 2, 3, etc., where m is the mass of the electron, v is the velocity of the electron, and r is the radius of the orbit. In the other words, angular momentum of electron in an atom is quantized. As long as the electron remains in a particular orbit, it does not lose or gain energy. This means that energy of an electron in a particular orbit remains constant. That is why these orbits are called stationary states. When energy from some external source is supplied to the electron, it may jump to some higher energy level by absorbing a definite amount of energy equal to the difference in the energy between the two energy levels. When the electron jumps back to the lower energy level, it radiates same amount of energy in the form of the photon of radiation. Delta E is equal to E2 minus E1 is equal to h nu. Nu is equal to E2 minus E1 by h, where nu is the frequency of the emitted radiation. Bohr's model for hydrogen atom. Quantization of energy and Bohr's model. According to the Bohr's model, energy of the electron in an atom is quantized. Quantization means that a quantity cannot vary continuously to have any arbitrary values, but can change only discontinuously to have some specific values. To illustrate this point, let us consider a simple example. Suppose a person moves down a staircase, then energy of the person changes discontinuously and he can have only certain definite values of energy corresponding to the energies of various steps. Energy of the person in this case is quantized. On the other hand, if the person moves down a ramp, then his energy changes continuously and he can have any value of energy corresponding to any point on the ramp. Energy in this case is not quantized. So, according to Bohr's model, energy of an electron in an atom is quantized. The main successes of Bohr's model are: Number 1. Bohr's model could explain the stability of an atom. Number 2. Bohr's theory helped in calculating energy of an electron in a particular orbit of hydrogen. The expression is En is equal to minus k square into 2 into pi square into m into e raised to the power 4 divided by n square into h square, where m is mass of the electron, e is charge on the electron, h is Planck's constant, k is Coulomb's law constant. On substituting the value of constants, we get En is equal to minus 1312 by n square kilojoule per mole. Bohr gives an expression for the radius of an orbit in hydrogen atom. Rn is equal to n square into h square divided by 4 into pi square into k into m into e square. Rn is equal to n square into 0.529 into 10 raised to minus 10 meter. Rn is equal to n square into 0.529 angstrom. Thus, as n increases, the radius of the orbit increases. The radius of first orbit of hydrogen is equal to 0.529 angstrom. This is also known as Bohr's radius. Explanation of line spectrum of hydrogen. In hydrogen atom, there is one electron which is present in first orbit in ground state. When energy is supplied, such as by passing electric discharge, this electron may be excited to some higher energy level. Since in a sample of hydrogen there are large number of atoms, the electrons in different atoms absorb different amounts of energies and are excited to different high energy levels. For example, let us consider the electron present in the fourth energy level, n is equal to 4, of different hydrogen atoms. In some atoms, it may come to ground state n is equal to 1 by direct jump, while in some others, it may first jump to second energy level n is equal to 2 and then to first energy level n is equal to 1, while in still others, it may come to ground state via third n is equal to 3 and second energy levels n is equal to 2. The lines which arise due to the transitions from high energy levels to first energy level are grouped as Lyman series. Similarly, the lines obtained as a result of transitions of electrons from high energy levels to second, third, fourth and fifth energy levels give rise to Balmer-Paschen bracket and Pfund series respectively. Suppose an electron from a higher orbit having n is equal to n2 jumps to a lower energy level having n is equal to n1 in hydrogen atom. As a result of this transition, the electron emits energy in the form of a photon radiation. Then the frequency of the emitted photon is frequency is equal to 3.29 into 10 raised to the power 15 into 1 by n1 square minus 1 by n2 square per second. In terms of wave number, 109677 into 1 by n1 square minus 1 by n2 square per centimeter. Limitations of Bohr's model. Number 1. Bohr's model could not explain the spectra of atoms containing more than one electron. Number 2. In the presence of a magnetic field, each spectral lines get split up into closely spaced lines. This phenomenon, known as Zeeman effect, could not be explained by Bohr's model. Similarly, the splitting of spectral line under the effect of applied electric field, that is Stark effect, could not be explained by Bohr's model. Reasons for the failure of Bohr model. The wave character of the electron is not considered in Bohr model. An orbit can be defined only if both the exact position and the exact velocity of the electron at the same time are known. This is not possible according to the Heisenberg uncertainty principle. Bohr model of the hydrogen atom ignores dual behavior of matter and also contradicts Heisenberg uncertainty principle. Did you know? Atom smashing scientists reach highest ever recorded man-made temperature, 1 lakh times hotter than the sun's interior. Scientists there collided lead ions to create a searingly hot subatomic soup known as quark-glued plasma at about 5.5 trillion Celsius, the hottest temperature ever recorded in an experiment. Summary. Let us summarize what we have learnt. Electrons are negatively charged. Charge to mass ratio of electron is 1.76 into 10 raised to the power 8 coulombs per gram. Rutherford shows that most of the mass and all the positive charges of an atom is concentrated in a very small region called nucleus. Mass number A is equal to number of protons plus number of neutrons is equal to number of nucleons. According to Maxwell's wave theory of light, electric and magnetic fields are perpendicular to each other and also to the direction of propagation. An ideal black body is a perfect absorber and perfect emitter of radiation. The amount of energy associated with the quantum of radiation is proportional to the frequency of radiation, where h is a constant known as Planck's constant and is equal to 6.625 into 10 raised to the power minus 34 joule second. Photoelectric effect may be defined as the phenomenon of ejection of electrons from the surface of a metal when light of suitable frequency strikes it. The electrons thus ejected are called photoelectrons. Atomic spectrum of an element can be used to identify the element and is sometimes called fingerprint of its atom. The lines in the emission spectrum of hydrogen are classified into 5 series as follows: Lyman series, Balmer series, Paschen series, bracket series and Pfund series. Rydberg gave a general formula which is applicable to all the series in the hydrogen spectrum. The value 109677 per centimeter is called Rydberg constant for hydrogen. Bohr gives an expression for the radius of an orbit in hydrogen atom. Rn is equal to n square into 0.529 angstrom.